The quantum number which may be designated by SPDF instead of number is A, N, B, L, C, M, L, and D, MS. So, azimuthal quantum number, that is L, can be denoted by SPDF. So, we can write this as L is equal to 0 is S orbital, L is equal to 1 is P, L is equal to 2 is D, and L is equal to 3 is F. Hence, SPDF may be used instead of number. So, option B is the correct answer. The set of quantum numbers n equal to 4, L equal to 0, M equal to 0, n is S equal to plus half correspond to the most loosely bound ground state electron of which one of the following atoms? A sodium, B chlorine, C chromium, D rubidium. To find this, we have to know the electronic configuration, outermost electronic configuration of these atoms. So, more specifically, we will find the electronic configuration of chromium with atomic number 24, B 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, and 4s1. So we have given the principal quantum number which is equal to 4. Azimuthal quantum number is 0. So we have to write for 4s1. So n4, L0, M0, and S is equal to plus half is the correct configuration for chromium, option C. Orbital angular momentum for a d electron is A 6h upon 2 pi, B root of 6h upon 2 pi, C 12h upon 2 pi, D root of 12h upon 2 pi. So for this question, we know that L is equal to 2, that is azimuthal quantum number for D electron. So we can write this mu is equal to root of L into L plus 1 into h upon 2 pi. So mu is equal to root of 2 into 2 plus 1 into h upon 2 pi. On solving this, we get mu is equal to root of 6 h upon 2 pi. So option B will be the correct answer. Minimum de Broglie wavelength is associated with A electron, B proton, C CO2 molecule, D SO2 molecule. We know lambda is equal to h upon mv, which is momentum mv. For same velocity, wavelength is inversely proportional to mass. SO2 molecule has least wavelength because it has highest molecular mass. So option D is the correct answer. Calculate de Broglie wavelength of an electron traveling at 1% of the speed of the light. So 1% of the speed of the light will be V is equal to 1 upon 100, 3 into 10 raised to 8 meter per second, which is equal to 3 into 10 raised to 6 meter per second. Momentum of an electron is equal to mv. We can denote momentum by P. So mass of electron is 9.11 into 10 raised to minus 31 kg into 3 into 10 raised to 6 is the speed. So momentum will be 2.73 into 10 raised to minus 24 kg meter per second. So de Broglie wavelength of electron lambda will be h upon p, where h is 6.626 into 10 raised to minus 34 upon momentum as just found out as 2.73 into 10 raised to minus 24. On solving this, we get lambda is equal to 2.424 into 10 raised to minus 10 meter. So option B is the correct answer. The velocity of hydrogen molecule is 5 into 10 raised to 4 centimeter per second. Then de Broglie wavelength is A 2 angstrom, B 4 angstrom, C 8 angstrom, D 100 angstrom. According to de Broglie, lambda is equal to h upon mv. So substituting the values 6.26 into 10 raised to minus 27 erg per second, we are taking this in CGS unit. Mass be 2 upon 6.023 into 10 raised to 23 into 5 into 10 raised to 4 centimeter per second. On solving this, we get the value as 4 into 10 raised to minus 8 centimeter, which can be written as 4 angstrom unit. So option B is the correct answer. A 600 watt mercury lamp emits monochromatic radiation of wavelength 331.3 nanometer. How many photons are emitted from the lamp per second? So the given power is 600 watt and wavelength is equal to 331.3 nanometer. H is 6.626 into 10 raised to minus 34 joule second. C is the velocity of light, 3 into 10 raised to 8 meter per second, and time is given as 1 second as per second. So power is equal to energy upon time. Energy can be written as nhc upon lambda by t. Substituting the values of power is equal to 600 n into 6.62 into 10 raised to minus 34 into 3 into 10 raised to 8 lambda 331.3 into 10 raised to minus 9, as it is nanometer and time is 1 second. On solving this, we get n is equal to 1 into 10 raised to 21. So option C will be the correct answer. The circumference of the second Bohr orbit of electron in the hydrogen atom is 600 nanometer. Calculate the potential difference to which the electron has been subjected so the electron stops. The electron had the de Broglie wavelength corresponding to the circumference. So in this question, we know that n is equal to circumference upon wavelength. Therefore, n lambda is equal to 2 pi r. 2 pi r be the circumference, therefore 2 lambda is equal to 600. Therefore lambda is equal to 300 nanometer. Stopping potential is V0, so EV0 is equal to half mv square, which is kinetic energy. So we can write EV0 equal to half m, substituting the value of velocity as h upon lambda m the whole square. Therefore, V0 is equal to h square upon 2m lambda square e. Substituting the value of h as 6.626 into 10 raised to minus 34, mass as 9.1 into 10 raised to minus 31, which is the mass of electron, and 3 into 10 raised to minus 9 as the lambda, and 1.6 into 10 raised to minus 19 as the charge of electron. We get V0 as 1.675 into 10 raised to minus 5 volt. So option A will be the correct answer. The radius of first Bohr orbit or hydrogen is 0.53 angstrom. The radius of third Bohr orbit is A 0.79 angstrom, B 1.59 angstrom, C 3.15 angstrom, D 4.77 angstrom. We know that Rn is equal to R1 into n square. Therefore, third orbit, that is R3, which is equal to 0.53 into 3 square, 0.53 into 9, which is equal to 4.77 angstrom unit. So option D will be the correct answer. What is the energy in EV required to excite the electron from N1 to N2 state of hydrogen atom? According to Bohr equation, E2 minus E1 is equal to 13.6 1 upon N2 square minus 1 upon N1 square. Therefore, delta E is equal to 13.6 1 upon 1 minus 1 upon 4, the second orbital and first orbital. On solving this, we get 10.2 eV as the answer. So option D is the correct answer. 1 mole of photon, each frequency 2500 per second, would have approximately a total energy of. So in this particular question, we know that frequency is equal to 2500 per second. Energy is equal to h nu, we can find energy 6.626 into 10 raised to minus 34 into 2500. Energy will be in joules. So energy of 1 mole, to find the energy of 1 mole, we have to multiply this with Avogadro number, which is 6.023 into 10 raised to 23. Now, to find the energy in ergs, we get answer as 9.977 into 10 raised to minus 7 joules. So, which is approximately equal to 10 erg energy, as 1 joule is equal to 10 raised to minus 7 ergs. So option A is the correct answer. The ratio of area covered by second orbit to the first orbit is, we know that Rn is directly proportional to n square. Therefore, An will be directly proportional to n raised to 4. Therefore, A2 upon A1 is equal to N2 upon N1 the whole raised to 4. So second orbit will be 2 raised to 4, 1 raised to 4, which is equal to 16 is to 1. So option D is the correct answer. An isotone of Ge having atomic number 32 and mass 76 is. So isotones. What are isotones? Isotones are the species which have equal number of neutrons. Hence, Ge with atomic number 32 and atomic mass 76. So their neutron number is 44. Astatinium As will have 33 as the atomic number and 77 as their mass. On difference, we get the neutron number as 44. So these two are isotones of each other. Option B. The value of energy for the first excited state of hydrogen atom will be A minus 13.6 eV, B minus 3.40 eV, C minus 1.51 eV, D minus 0.85 eV. So energy is equal to minus 13.6 upon n square eV. So we have to find in first excited state, which is second orbital, minus 13.6 divided by 2 square in EV, which is equal to minus 3.4 EV. So option B is the correct answer. A gas absorbs a photon of 355 nanometer and emits two wavelengths. If one emission is at 680 nanometer, the other is at. So we know that E is the total energy, which is equal to E1 plus E2. Hc upon lambda is equal to Hc upon lambda 1 plus Hc upon lambda 2. So we can write this as 1 upon lambda 1 plus 1 upon lambda 2. So substituting the values as 355, 1 upon 680 plus 1 upon lambda 2. On solving this, we get lambda 2 as 742.76 nanometer. So the approximate value is 743 nanometer, option C. If the de Broglie of a particle of a mass is 100 times its velocity, then the value in terms of mass and Planck's constant h is. Let wavelength of the particle be x. So velocity is equal to x upon 100. We know that lambda is equal to h upon mv, so we can write this as x is equal to h into 100 upon m into x. Therefore, taking square on both sides, x square is equal to 100 into h upon m. Therefore, x is equal to 10 root of h upon m. So option B is the correct answer. The radius of hydrogen atom is 0.53 angstrom. The radius of lithium Li2 plus is of. So we know that the radius of hydrogen is 0.53 angstrom. Lithium atomic number 3, 2 plus, has only 1 electron, but it has 3 protons in nucleus. Hence, the electron feels 3 times more attraction from nucleus in comparison of hydrogen atom. The radius of lithium 2 plus having 3 proton will be 0.53 upon 3, which is equal to 0.17 angstrom unit. So option B is the correct answer. The energy absorbed by each molecule of a substance is 4.4 into 10 raised to minus 19 joules, and the bond energy per molecule is 4 into 10 raised to minus 19 joule. The kinetic energy of the molecule per atom will be, we have to find kinetic energy per atom is equal to 4.4 into 10 raised to minus 19 minus 4 into 10 raised to minus 19 divided by 2. So we get 0.4 into 10 raised to minus 19 upon 2, which is equal to 2 into 10 raised to minus 20. Option A is the correct answer. The wave number of the spectral line is the emission spectrum of hydrogen atom is equal to 8 by 9 times the Rydberg constant if the electron jumps from. According to Rydberg's formula, V bar is equal to R upon 1 upon N1 square minus 1 upon N2 square into Z square. So we know that the emission spectrum is equal to 8 by 9 times R. Then N1 should be equal to 1 and N2 should be equal to 3. So Rydberg constant formula will becomes R 1 upon 1 square minus 1 upon 3 square into 1 square. So on solving this, we get R here 9 minus 1 upon 9. So 8 by 9 upon R. So N equal to 3 and N1 equal to 1 is the correct option. Option A. Is the maximum number of emission line obtained when the excited electron of a hydrogen atom in N5 drops to the ground state. Number of emission line in the spectrum will be equal to N2 minus N1 into N2 minus N1 plus 1 divided by 2, where N2 is equal to 5, N1 is equal to 1. 5 minus 1 into 5 minus 1 plus 1 divided by 2, which is equal to 20 upon 2, 10 lines. So option A is the correct answer. The energy of electron in third orbit of an atom is minus E. The energy of electron in first orbit will be. So we have to find E3 is equal to minus E, which is minus 13.6 into Z square upon 3 square. Therefore, minus E can be written as E0 into Z square upon 9, where E0 is 13.6. Therefore, E0 is equal to minus 9E upon Z square. According to the question, E1 is equal to minus 13.6 into Z square upon 1 square. So, it becomes E0 into Z square. So we can write this as substituting the value of E0 minus 9E upon Z square into Z square, which is equal to minus 9E, E1. So option D is the correct answer. What is the frequency of photon whose momentum is 1.1 into 10 raised to minus 23 kg meter per second square? So we know that E is equal to mc square. So we can write E is equal to h nu as well. Therefore, mc square is equal to h nu. Therefore, nu is equal to mc square upon h. Substituting the values of mass and then velocity, h 6.6 into 10 raised to minus 24. On solving this, we get frequency as 5 into 10 raised to 18 hertz. So option D is the correct answer. One would expect proton to have very large A. ionization potential, B. radius, C. charge, D. hydration energy. H plus ion will have very large hydration energy due to very small ionic size. Ionic size of H plus ion is very small as it is the first atom of the periodic table. So hydration energy is inversely proportional to the size, while rest other is directly proportional. So option D is the correct answer. Density of a nucleus of an atom is. So the nucleus of an atom, we have to find the density. The simple formula for density is mass upon volume. But we have to know the mass of the nucleus, which is approximately measured in AMU, which is equal to 1.66 into 10 raised to minus 24 kg. This is a constant value which we have to remember. The mass and the radius of the nucleus is also a constant value, which is 1.2 into 10 raised to minus 15 angstrom unit. So these are the values of mass and radius of which we can find density. So we can substitute value as density is equal to atomic mass upon volume, which is equal to 4 by 3 pi r cube. R cube we have to substitute the values of radius here. So atomic mass will be 1.66 into 10 raised to minus 24 kg divided by 4 by 3, which we can write as 1.33 pi r cube as 1.2 into 10 raised to minus 15 cube here meter cube. On solving this, we get density is equal to 2.4 into 10 raised to 17 kg per meter cube. So option C is the correct answer. An atom has electronic configuration of 1s to 2s to 2p6, 3s to 3p6, 3d10, 4s to 4p5. Atomic weight is 80, the atomic number is, and the number of neutrons in the nucleus is. So in the nucleus there are neutrons and protons, and we have to find the atomic number. So as the atomic weight is 80, we can conclude that the atom will be bromine with atomic number 35 and weight 80. So atomic number A is 80, Z is 35. So we have to find now the N, which is the number of neutrons. So N is equal to A minus Z is equal to 80 minus 35, which is 45. So atomic number is, that is number of protons is 35 and the number of neutrons is 45. So option A is the correct answer. Sodium ion Na plus ion is isoelectronic with A lithium ion, B magnesium, C calcium ion, D barium ion. Okay, for isoelectronic species, the number of electrons present in the species should be same. So sodium ion will have how many electrons? Atomic number of sodium is 11 and plus 1 charge is there, that is 1 electron is removed, so minus 1, which is equal to 10 electrons. Of all the species, magnesium ion, atomic number of magnesium is 12 and 2 electrons are removed plus 2 charge, so minus 2, which is equal to 10. As Na plus and Mg2 plus ion both have 10 electrons each, so both are isoelectronic species. Option B. Energy of electron of hydrogen atom in second Bohr orbit is. So the basic formula for energy of electron is equal to minus 2.172 into 10 raised to minus 18 divided by n square, where n is the number orbital in which the electron is. So here is the second Bohr orbital, so n is equal to 2, so we can write this 2.172 into 10 raised to minus 18 2 square. On solving this, we get energy as minus 5.44 into 10 raised to minus 19 joules. So option A is the correct answer. The wavelength of radiation emitted when in a hydrogen atom electron falls from infinity to stationary state 1 would be, where R is Rydberg constant is equal to 1.097 into 10 raised to 7 per meter. The formula for wavelength is 1 by lambda is equal to R 1 upon n1 square minus 1 upon n2 square. So here 1 upon lambda is equal to, substituting the value of R and the orbit, first orbit, and it comes from infinity, so second orbit is infinity square. This becomes 0, so lambda is equal to 91 into 10 raised to minus 9 meter. We know 10 raised to minus 9 is equal to 1 nanometer. Therefore, wavelength lambda is equal to 91 nanometer. So option C is the correct answer. Which transition in hydrogen atom spectrum will have same wavelength as the transition n equal to 4 to n equal to 2 of helium spectrum? For He plus ion, 1 upon wavelength is equal to z square r upon 1 upon n1 square minus 1 upon n2 square is the basic formula. So for helium ion, z is equal to 2, so we can substitute value for z. n1 becomes 2 square minus n2 becomes 4 square, which is given in question. So 1 upon lambda is equal to 3r by 4. As the wavelength is same, so we can substitute for hydrogen atom. This is for helium. Now for hydrogen, 1 upon lambda is equal to r 1 upon n1 square minus 1 upon n2 square, which is the mandatory formula. Substituting 1 upon lambda is this, so 3r by 4 is equal to r into 1 upon n1 square minus 1 upon n2 square. On solving this, we get 1 upon n1 square minus 1 upon n2 square is equal to 3 by 4. Therefore, n1 is equal to 1 and n2 is equal to 2. So option E will be the correct answer. The energy required to break 1 mole of Cl-Cl bond in chlorine is 242 kilojoule per mole. The longest wavelength of light capable of breaking a single Cl-Cl bond is, where C is given as speed of light 3 into 10 raised to 8 meter per second and Avogadro number Na is given. Since for 1 mole of chlorine, energy required is 242 into 10 raised to 3 joules. Therefore, for 1 molecule of chlorine, energy required is equal to 242 into 10 raised to 3 divided by Avogadro number. This is the energy for 1 molecule. Since energy is also equal to Hc upon lambda, we can equate 242 into 10 raised to 3 divided by 6.02 into 10 raised to 23 equal to 6.6 into 10 raised to minus 34, which is Planck's constant, into 3 into 10 raised to 8 divided by wavelength. We have to find wavelength on cross multiplying, and solving this we get wavelength equal to 0.494 into 10 raised to minus 6 meter. On solving we get lambda is equal to 494 nanometer. So option A is the correct answer.